Good evening, ladies and gentlemen. How are you guys doing? I'm glad you guys are doing well, and I see much better than last week. I'm also well, thank you. So I assume you guys have much less tests and assignments this week. Ah, you will get those weeks where it seems that everything happens in the same week. So not for you, so I assume this is a bad week for you. Why? What is happening next week? Ish. Okay, I know that feeling. I were in your shoes not that long ago, so I completely understand if you had a bad test schedule. It's a lot of physics assignments and tests this week. Yes, that is one thing. I don't know why, but the scheduling of tests is out of the lecturers and department's hands. That's handled by the registrar of the university and the registrar's office. And sometimes you get out a bad end, sometimes the scheduling is not too bad. I remember my worst exam schedule was in my second year. There I wrote calculus 2 the Friday morning, physics 2 calculus 2 the Friday morning, uh, physics to the Friday afternoon, and applied mathematics to the Saturday morning. That was my most harsh examination timetable ever. So everyone goes through these sorts of hiccups. But you are not alone in this. So this week and next week will be also busy weeks for me because I'm trying to push to get my research out. So there's a lot of editing going into that as well. So I'm with you this week and next week on working long hours and a lot of early mornings and late nights. So let's start off with tonight's lecture. So since last night we ended off and we now have an overview of the family of stars. We know star classifications. We know how temperature and luminosity and the diameter of a star relates to one another and why that is important. So now we're going to start looking at how these stars are formed and what are these structures inside stars and what govern the structures in stars. So for this, we need to understand the interstellar medium, making stars from the interstellar medium, young stellar objects and protostellar disks, stellar structure and nuclear fusion, and then we're going to end off tonight with main sequence stars. But to get a little bit of an overview of how this fits together and just for you to understand a bit more of the topics as we go through them tonight, I'm going to show you guys a short video.
Stars in the sky look pretty, flickering intense diamonds dotting the velvety night. But make no mistake, they are churning cauldrons of violence, barely constrained thermonuclear generators, creating enough energy to vaporize the Earth 1,000 times over. Their lives depend on it. Heck, our lives depend on it. But in their case, how they live and how long they live depends on that creation of energy. And in this universe, nothing lasts forever. Very roughly speaking, we can divide stars into two groups, low mass stars and high mass stars. That line lies around 8 times the mass of the sun, and the reason for that is something we'll get to shortly. Things get very exciting at the high end, but for now, let's take a look at the low mass end of the scale. Things are simpler there. Stars make energy in their cores by fusing hydrogen into helium. This is actually a pretty complicated process with lots of steps, but in the end, 4 protons plus some other ingredients get turned into one helium nucleus. Each time this happens, a little bit of energy is released, but in the core of a star, it happens countless times every second. It adds up to a lot of energy, enough to power a star, in fact. The rate at which hydrogen fusion occurs depends on how much pressure the star has in its core. A higher mass star squeezes hydrogen harder, so it fuses far more quickly. The rate is so much higher, in fact, that even though they're a lot bigger than low mass stars, high mass stars run out of hydrogen fuel in their cores more quickly. The lower mass a star is, the longer it lives. In the lowest mass stars, cool red dwarfs, the rate is so slow they last a long, long time. But there's more to it than that. They fuse hydrogen only in their very centers, and their cores aren't very big. Outside of this small region, the gas is convective, which means the hot stuff rises all the way to the surface, cools, then falls back to the core. That's important because it means the entire star is available for fuel. Both hydrogen and helium rise up through the star and then fall back down. The star can't fuse the helium, but the hydrogen that makes it back to the center is just more grist for the mill. Even after a long, long time, these stars can still shine as the hydrogen mixed throughout the star eventually makes it down to the center. So how long can a really low mass red dwarf last? 1 trillion years. 1 trillion! The universe itself is less than 14 billion years old. So even the oldest red dwarf stars are basically infants. They're just barely getting a start in life, and they'll look pretty much the same for the next, 990 billion years or so. Eventually, though, they do run out of fuel. When one does, the star itself will be nearly pure helium, plus whatever heavier elements it was born with, and fusion will cease. It'll then cool, which will take many more billions of years. Finally, it'll be a cold, black, dead star, and for them, that'll be pretty much that. Or so we think. The universe is far too young for any of these red dwarfs to have run out of fuel yet. That's true for stars at the lower end of the mass scale, up to roughly 1/3 of the mass of the sun. But stars with more mass than that, stars more like the sun itself, work a little differently. Their cores are bigger and hotter and denser. The different conditions inside them means the material in them doesn't convect. The hot stuff doesn't rise away from the core. What's in the core stays in the core. Outside the core, there's a very deep and active convection zone, but that doesn't interact with the material in the core itself. This means that not only do stars near the sun's mass use up their fuel more quickly than red dwarfs, they have relatively less fuel to work with as well. Depending on their mass, their lives aren't nearly as long. For the sun, that total lifespan is about 12 billion years, give or take. The sun is nearly 5 billion years old now, so it's approaching middle age. Its life is similar to other stars of similar mass, so let's take a look into the far future. Will our sun go gently into that good night? Ever since the sun was born, it's been fusing hydrogen into helium in its core. The helium is trapped there, unable to be used as fuel, and it's building up in the core like ash in a fireplace. As it does, the density in the sun's core slowly increases. When you compress a gas, it heats up. That means every day the sun's core gets a wee bit hotter. That extra heat works its way out through our star, heating up the outer layers too. A hotter gas shines more brightly, so the sun has been steadily increasing in brightness too. It's an incredibly slow but inexorable process. The sun's increased in luminosity by about 40% since it was born, and it's not done. Helium is still building up in its core, and eventually it'll run out of hydrogen to fuse. Without fuel, fusion in the core will stop, Helium can be fused into carbon and a little bit of oxygen and neon, but it has to be incredibly hot to do so, and the sun's core won't be anywhere near those conditions. Still, half the sun's mass is bearing down on the core, so even though fusion stops, the core will continue to contract and heat up. It'll get so hot that the temperature outside the core will get to hydrogen fusion temperatures. Like igniting a match by holding it near a flame, the hydrogen outside the core will start to fuse. That'll occur in a shell surrounding the core, adding its heat to the outer layers of the sun as well. When you heat a gas, it expands. The sun's outer layers will do just that, and our star will grow to well over twice its current size. Astronomers call a star like this a subgiant. Not only will it grow, but its color will change. The sun will be giving off more total energy than it does now, but its surface area will increase so much that the amount of energy radiated per square centimeter will go down. There'll just be a lot more square centimeters. This means, ironically, that the surface will actually cool. The sun's temperature will go down. Cooler stars are red, and so the sun will be too. But the core still isn't done. The details are complicated, but the core continues to contract and heat up. It gets so hot that the outer layers swell even more, and the sun can bloat up to a fantastic 10 to 150 times its present size. It will then be a red giant. Red giants are fantastically bright because of all the energy percolating up from their interiors, coupled with their enormous size. When it turns into a red giant, the sun will increase its luminosity by an incredible 2,000 times. That huge increase in luminosity does more than just make the sun bright, though. As a red giant, the sun will be so swollen that the gravity at its surface will drop substantially from what it is now. The force of gravity holding it down is weak, but the force from all that light blasting out from below is strong, easily overpowering gravity. Material on the surface will get blown off like a leaf in a hurricane. Think of it as a super solar wind. That means the sun will shed mass a lot faster than it does now. While it's a red giant, it'll lose fully a third of its mass. At some point, the core contracts and heats up so much that the conditions will finally be primed for helium fusion. Suddenly, helium is converted into carbon, releasing a lot of energy. In a weird twist, due to a lot of very complicated physics, the core itself winds up expanding, absorbing most of that energy. In the end, less energy is pumped into the outer layers, so the sun's outer layers contract. The sun shrinks. The outer layers get dense again, which warms them up a bit, and the sun turns from red to orange. It's still pretty big, more than 10 times its current day size, and puts out 20 to 50 times as much energy as it does now. But then we see a sort of reboot of what's happened in the core before. This time, though, helium is fusing in the core, and the carbon is building up like ash. Once again, the core starts to contract and heat up. This dumps more energy into the outer layers, they expand and cool, and the sun turns into a red giant again. This time, it's even brighter and bigger and loses even more mass, shedding over half of what's left. In the meantime, helium fusion isn't very stable, to say the least. It swings wildly, increasing and decreasing its rate by huge amounts on very short timescales. The sun will probably undergo a series of tremendous paroxysms, epic eruptions as the helium fusion spikes, creating huge surges in energy production. It'll lose even more mass each time. Finally, though, we approach the end game. The sun doesn't have enough mass to squeeze carbon atoms enough to fuse them. They build up in the core until there's no more helium and fusion stops. On top of that, well, there's nothing on top of that. By this time, the sun will have literally blown off all its outer layers. It's essentially a naked core, a hot, intensely bright, super compact ball, not much bigger than Earth. We call this a white dwarf. Its fate is sealed. It can't generate energy, so it'll cool and fade over the next few tens of billions of years. At that point, we can safely say the sun is dead. But that's not always the case for all stars. Some with more mass than the sun still go through another phase before dying. They form what are called planetary nebulae, and these are so amazing and beautiful that they rate their own episode, which, along with more fun stuff about white dwarfs, we'll get to next time. So that's it for the sun. But what about us? Of course, the Earth won't fare very well during all this. It'll get cooked before the sun even becomes a subgiant, and by the time the sun is a red giant, we'll be good and fried. The average temperature on our planet will be so high that it'll melt rocks, and in a sense, it'll look much like it once did so many billions of years before, when it first formed, a molten ball of rock. But it gets worse. When the sun expands, it'll reach a radius very close to the size of the Earth's orbit now. Does that mean our planet itself will be consumed by the sun? Maybe not. As the sun expands, remember, it loses mass. That means its gravitational pull will weaken, and Earth will move out from the sun into a bigger orbit. If things work out right for us, the Earth will back off faster than the sun expands, and we'll avoid finding out what it's like to be inside a star. Due to a quirk of physics, if the sun loses more than half its mass, its gravity will decrease so much the planets will no longer be gravitationally bound to it, and they'll be flung into interstellar space. I'm not sure that's any better for us. Either way, the Earth will have been long dead, and hopefully humanity will have figured out the trick to interstellar travel by that time. All those Earth-like exoplanets around younger stars will look pretty nice in a billion years or two. Mind you, this isn't happening anytime soon. The Sun won't become a subgiant until it's nearly 11 billion years old, over 6 billion years from now. The first red giant stage happens when it's over 11.5 billion years old, and the second stage a half billion years later. This is a long, long time coming. If the sun had more mass, it could avoid this fate. A star with about 8 times the sun's mass can. It has enough mass to squeeze those carbon nuclei hard enough to fuse them together. Those high mass stars have a much different and far more explosive fate than lower mass stars like the sun. And trust me, we'll cover that in lots of fun detail soon. And while this all sounds very bleak, not all is lost. This is all part of the natural cycle of the universe. And in fact, we wouldn't be here at all if it weren't for the way stars live and die. Be thankful for what you have, and that we can not only observe it, but understand it too. Today you learned that very low mass stars live.
So hopefully this gives a bit of an overview of what tonight's lecture is going to be about. So question, if this happens to Sol, then what would happen to low mass red giants? Would they grow and eventually become white dwarfs as well? Yes, and that is actually something we are going to discuss in the following chapter. So there is a point where you get to a certain mass, everything above that mass, a certain thing happens to the star, everything below that mass, a certain thing happens to the star. And tonight's lecture will be an intro to it. So the first couple of slides, so yes, black hole versus white dwarf, and that's going to happen. And also third star classification is pulsars. So I'm going to show the first couple of slides. I'm just going to show in Google Slides because there's a few animations I want to show you. And for some reason, we can't see it on Blackboard. So, can everyone see these slides? Okay, cool. So, like I said, in the previous chapters, we discovered a wide range of differences within the family of stars. In this chapter, you will combine observations and hypotheses to understand how nature makes stars and learn the answers to 5 important questions. These questions are: how do astronomers study the gas and dust between the stars, called the interstellar medium? Secondly, how do stars form from the interstellar medium? Thirdly, how do stars remain stable? Number 4, how do stars make energy? And then lastly, why do the luminosities and lifetimes of stars depend on their mass? The stars are not eternal, so when you look at the sky, you see hundreds of points of light, and amazingly enough, each one, like the sun, is a tremendous nuclear fusion reactor held together by its own gravity. So the stars you see tonight are the same stars your parents, grandparents, and great-grandparents saw. Stars don't change precipitously in a person's lifetime, or even during all of human history, but they do not last forever. Stars are born. So when I speak of the death of stars, it's not this Death Star. It is rather something like this. And how can you know what the life cycles and internal processes of stars are, given that you won't live long enough to see them evolve? And you can't see inside them. So the answer lies in the methods of science. By constructing hypotheses about how nature works and then testing those hypotheses against evidence from observations, you can unravel some of nature's greatest secrets. So now I'm going to swap over back to Blackboard. So when people use the phrase the vacuum of space, they reveal a common misconception that space is empty. Space is not empty. There is gas and dust between the stars, called the interstellar medium. So here we can see, for example, if you look at the Orion Nebula, on the image on the left, invisible wavelengths through an optical telescope. This is what we'll see, and we can see the Orion Nebula. But if we look to the same area in space through an infrared telescope, we can see the swirling clouds of gas and dust that forms the interstellar medium. And we can also here see the core of the Orion Nebula and the star-forming region inside the Orion Nebula. That is actually very, very cool. So one way to investigate properties of interstellar medium is to measure its effects on the starlight that passes through it. Astronomers observe that distant stars appear fainter than they shoot for their distances and luminosities. So that is estimated from their spectral types. This effect is called interstellar extinction. Distant stars also appear redder than they shoot for their spectral type. For example, some distant O stars actually look red rather than blue. This effect is called interstellar reddening, and is the result of interstellar extinction being stronger for short wavelength light than for long wavelength light. In fact, the interstellar medium is nearly transparent at near infrared wavelengths, allowing astronomers to look into and through interstellar clouds that are so dense they completely block our view at visible wavelengths. Another way astronomers detect material in the interstellar medium is by observing interstellar absorption lines in the spectra of stars. You can be sure that the interstellar absorption lines are not spectral lines of the stars themselves for several reasons. For example, some distant O stars show calcium and sodium lines. Those stars are too hot for them to form those lines in their own atmospheres. Those absorption lines must be produced instead by atoms located between the stars and Earth. So here we can see an image A. Interstellar reddening makes stars seen through a cloud of gas and dust look redder than they should because shorter wavelength light is more easily scattered. Then in image B, no stars are detected at visual wavelengths through the dense cloud except near the edges. And then in image C, at longer near-infrared wavelengths, many stars can be detected behind the cloud. And then in image D, interstellar spectral absorption lines can be recognized because they are very narrow. Here, a spectral line produced in the atmosphere of a star is magnified so that it is seen as a broad dip in the plot. In contrast, absorption lines produced by two clouds in the interstellar medium are much narrower. The widths of interstellar lines also give away their origins. In the atmosphere of the star, the gas is so dense that atoms collide with each other often, disturbing the electron energy levels, and so hot that atoms move rapidly, producing Doppler shifts. Both of those effects broaden or blur spectral lines from stellar atmospheres. In contrast, much of the interstellar gas is cold and its density is very low, typically about 1 atom per cubic centimeter, although the density can be much higher in dense clouds. Even there, gas is 1 times 10 to the power 15 times less dense than the air you breathe. Because atoms in the interstellar medium move slowly and collide only rarely, interstellar absorption lines are extremely narrow. So here we can see the broad stellar line, and here we can see the narrow interstellar lines. Spectroscopy tells you the abundance of elements in the interstellar medium. About 70% of the mass of interstellar gas is hydrogen, 28% is helium, and 2% is made up of elements heavier than helium. The atoms are joined together to form molecules in the densest, coldest interstellar clouds, which are called molecular clouds. Astronomers have detected more than 150 different molecules in the interstellar medium. Almost all of the material in the interstellar medium is gas, but about 1% of the mass is made up of dust particles called interstellar dust. Studies of interstellar spectra reveal that dust particles are composed of carbon, silicates, iron, ice, and organic compounds. Note that organic compounds are molecules based on multiple linked carbon atoms, which do not have to originate with living things. Details of interstellar extinction and reading shows that the particles are almost all less than 1 micron, so 1 times 10 to the power minus 6 meters, or basically 1,000 nanometers in diameter. You can expect that if interstellar gas atoms are viewed against a dark or cold background, rather than in front of the hot, bright background of stars' photosphere, those atoms can produce an emission spectrum. Interstellar emission lines, like absorption lines, allow astronomers to study that gas and dust between the stars. Cold neutral hydrogen floating in space produces a prominent emission line at a wavelength that can be detected with radio telescopes. This is due to the fact that electrons and photons have tiny magnetic fields, because they are charged particles that is also spinning. So here we can see protons and electrons spin and consequently have small magnetic fields. Because they have opposite electrical charges, they have opposite magnetic fields if they spin in the same direction. If they spin in opposite directions, their magnetic fields are parallel. As explained in the text, neutral hydrogen atoms flipping from the parallel to the antiparallel state emit radio photons with a wavelength of 21 centimeters. Astronomers can use the resulting hydrogen 21 centimeter radio line to map the location of the cold, low-density gas in our galaxy. And this is how it will look like. So here we can see the 21 centimeter radio observations reveal many clouds of neutral hydrogen orbiting the center of the galaxy. So can anyone guess why we are seeing the center of our galaxy in this way? Yes, so why does it look like it is like almost we're seeing a bright bar? Because we are looking to the center of our galaxy. So for example, if you take a plate and you pick it up and you look directly to the side of the plate or even a frisbee, we see that thin edge of the plate. So we're not looking on from the top or the bottom, but we're looking exactly at the side. So we are looking through the entire galaxy, and that is why we see this bright emission line. But we can also take an infrared image of our galaxy. And here we can see location of clouds of cold interstellar gas and dust, and that is visible due to radiation from the dust grains. And we can take a picture of the visual wavelengths of the center of our galaxy. So here we can see it edge on straight in the visual part of the spectrum. We can also take an X-ray image of our galaxy. So here we can see the location of very hot. So the brighter it is, the more hot the X-rays is produced. And those X-rays are usually produced in supernova explosions and basically at the stages where stars are at the end of their life and starting to dying and becomes supernova. So, does anyone recognize this constellation and a nebula? Yes, this is the Orion Nebula and one of my favorite objects to actually observe. Yes, I think that is Mr. Erasmus took a photo of it through his telescope. But what can you guys tell me about nebula? Yes, stars are formed in these nebula. So, for example, the Orion Nebula, this nebula is also known as a stellar nursery. Yes, they are large clouds of interstellar dust. Do you guys recognize this nebula? Yes, Mr. Joshua. Can you tell us a bit more about it, perhaps, if you're willing? So yes, this is a planetary nebula, and you are right, it's the leftover of dead stars. And this one is called the Crab Nebula. And you guys recognize this nebula? Yes, you are correct. That is the Horsehead Nebula, also a very beautiful nebula. And here you can see this one as well. So where does this names come from? These names come from, so they have a official resignation. This is called the Horsehead Nebula because this looks like a horse's head. Yes, this looks like an hourglass. So that's something we will discuss later why this is forming. But this basically looks like an eye, right? And an hourglass. So there are three important things we need to understand and take note of when talking about nebula. So the H2 regions, so hydrogen 2 regions, are clouds of gas ionized by ultraviolet radiation from nearby hot stars. They are often called emission nebula because the ionized hydrogen produces visible wavelength photons that make the regions glow with a characteristic pink color. Secondly, if nearby stars are not hot enough to ionize the hydrogen in a nebula, it may still be visible as a reflection nebula produced when light is scattered by tiny dust particles mixed in with the gas. Then number three, at visual wavelengths, dark nebulae are visible where dense clouds of gas and dust are silhouetted against background regions filled with stars or bright nebulae. The key to understanding star formation is realizing the relation between young stars and the densest parts of the interstellar medium. So here we can see the visual and infrared images combined of the NGC 346 nebula. So this is a giant molecular cloud that began to collapse and form stars a few million years ago, including three massive star clusters visible in this image. So here we can see the intense outflows from gas of the hottest, most luminous of those stars is exciting some of its gases to glow as an emission nebula, and it's eating into the remaining dark molecules cloud at the right and lower right. So the NGC 346 nebula is located in a small Magellantic Cloud, a satellite galaxy of the Milky Way, about 60,000 parsecs, or 200,000 light years from Earth. Are you guys familiar with the small and large Magellantic Clouds? So the small and large Magellantic Clouds are two very small galaxies, referred to as satellite galaxies that orbits around our Milky Way galaxy. So when you are in a southern hemisphere and you are at a very, very, very dark place, so ideally in the Karoo, and you look south close to the horizon on a clear night, you would see something like two small clouds. But in fact, those are not clouds. Those are the small and large Magellantic Clouds that you can see. And when you look through a pair of binoculars or small telescope, then you can actually see it is a galaxy. But the only the nearest proper galaxy to us is the Andromeda Galaxy, but the small and large Magellantic Clouds are referred to as satellite galaxies. So spectra of the interstellar medium shows that its chemical composition is basically the same as that of hot stars. By observing at far infrared and radio wavelengths, to which interstellar dust is nearly transparent, astronomers can peer inside even dense molecular clouds and find evidence that stars are forming there. In fact, the largest molecular clouds are each massive enough to make thousands of new stars. Nevertheless, such a cloud can form into stars only if small portions of the cloud can be compressed somehow to high density and high temperature. At least four factors resist the compression of an interstellar gas cloud. And those factors must be overcome by gravity before star formation can begin. So let's take a look at these four principles that needs to be overcome before star can begin forming. So firstly, thermal energy in the gas appears as motion of the atoms and molecules. This thermal motion would make the cloud come apart if gravity were too weak to hold it together. Then secondly, the interstellar medium is filled with magnetic fields. Ionized atoms having an electric charge cannot move freely through a magnetic field. Although the gas as a molecular cloud is mostly neutral, some ions are included. And that means a magnetic field can exert a force on the gas as a whole. So gravity must overcome the interstellar magnetic field to make the gas contract. Thirdly, everything in the universe rotates. As a gas cloud begins to contract, it spins more and more rapidly, just as ice skaters spin faster as they pull in their arms. This rotation can become so rapid that it resists further contraction of the cloud. Then fourthly, turbulence in the interstellar medium can prevent the cloud from contracting. Many nebulae are observed to be distorted and twisted by strong turbulent currents that can prevent the cloud from contracting. So given these four resisting factors, it may seem surprising that any molecular clouds can contract at all. But both theory and observation suggest that such clouds can be triggered to form stars by effects such as passing shock waves, sometimes called a shock, the astronomical equivalent of a sonic boom. During such a triggering event, some regions of the large cloud can be compressed to such high densities that the resisting factors can no longer effectively oppose gravity and star formation begins. So here we can see how birth of a star and its molecular clouds can be initiated. So here we can see a shock wave in red, or a shock approaches the interstellar gas cloud. The shock wave passes through and compresses the cloud. Motions in the cloud continue after the shock wave passes. Then the densest parts of the cloud become gravitationally unstable. And then contraction regions of gas give birth to stars. So shock waves that can trigger star formation are common in the interstellar medium. For example, gas flows of several sorts produce shocks when they push into colder, dense interstellar matter. The ignition of very hot stars ionizes nearby gas and causes it to flow rapidly away, and new stars of all types seem to emit strong winds and jets while they are forming. Supernova explosions create powerful shock waves that rush through the interstellar medium as well. So here in image A, we can see nebula RCW79 is a bubble of intense hot gas about 70 light years in diameter. It was produced over the last million years as hot gas and radiation flowed away from the massive hot stars near the center of the bubble. Then in image B, millions of years ago, a massive star exploded as supernova in the upper left quarter of this image. And hot gas from that explosion is now pushing into cooler gas and causing the condensation of dust, which radiates strongly at infrared wavelengths. So here we can see new star formation is triggered by the companion, and here we can see dust condenses where the gas is compressed. So here we can see the stars will form in this compressed region. And here we can see the location of the supernova explosion, and that caused star formation in the interstellar medium. And the next topic we are going to discuss are protostars. So you can understand how low density clouds of interstellar gas might contract to become as dense as stars. But how does the cold gas become hot enough to be a star? The answer once again is gravity. To see how gravity can heat a gas, shift your attention to one dense cloud core destined to become a single star. Once that small cloud of gas begins to contract, gravity causes those atoms to fall towards the center, gaining speed as they go. Astronomers refer to this early stage in the star formation as free fall collapse. By the time the atoms have fallen most of the way to the center of the cloud, they are traveling rapidly. The atoms begin to collide with one another and convert their inward motion to jumbled random motion of thermal energy, causing the temperature of the gas to increase. When the contracting core becomes hot enough, it produces short wavelength radiation to which the core is not transparent. Then the core's thermal energy can no longer escape. and it enters a new stage of slow rather than freefall contraction. Although the term is used rather loosely by astronomers, a protostar can be defined as a stellar mass object that is compressed and hot enough to be opaque to the radiation it is emitting internally, but not yet compressed and hot enough to be able to generate energy by nuclear fusion, as would a main sequence star. Instead, a protostar shines with energy released gravitationally from a combination of matter falling inward to the protostar, plus slow contraction of the protostar itself. The protostar continues growing deep inside a surrounding cloud of cold, dusty gas. Those enveloping clouds have been called cocoons because they hide the forming protostar from view. So here we can see in this HR diagram has been extended to very low temperatures to show systematically the contraction of a dim, cool protostar. Then in image B, protostars are normally invisible at visual wavelengths because they are cool objects and are deep inside dusty clouds of gas, but they are detectable at infrared wavelengths. So here when we go to cool side at 100 Kelvin, here we can see where protostars are formed and they start to glow in the infrared. So protostar begins as an invisible concentration of cold gas deep inside a cloud, but as soon as it gets more energy, it starts to radiate infrared, and that eventually will end up on the main sequence. So protostars are not easy to observe. Astronomers calculate that a protostar stage is less than 1% of the lifetime of a star like the Sun. And although that is a long time in human terms, you cannot expect to catch many stars in the protostar stage. Furthermore, protostars form deep inside clouds of dusty gas that block your view at visible wavelengths, and being cooler than full-fledged stars, they produce radiation primarily at longer wavelengths. Astronomers must therefore depend on observations at infrared radio wavelengths to search for protostars in the natural environment. So, question. So, protostars are also the stars that spin very quickly, if I remember correctly. No, so stars that spin very fast are neutron stars, so more precisely, pulsar, that is a form of neutron star, but we are going to discuss that in a following chapter as well. So at the center of the Orion Nebula, also known as Messier 42, have a guys told you about a story of Messier objects? So let me get my bearings straight and I will tell you a bit about, so this is something interesting. So the Messier objects is named after the astronomer Charles Messier. And he was a French astronomer. So what Charles Messier did is when he wanted to catalog the night sky and all the objects that he could see with his naked eye and through his telescope that he had, he gave them a designation Messier 1, Messier 2, Messier 3, Messier 4. And I think currently there are about 110 Messier objects. So now there are a lot of other classifications that's being used, but out of traditionally, the Messier classification still exists. But there's a competition each year to see who can firstly observe and record all 110 Messier objects in one night. And that is actually quite tricky because you have to be at the correct location, that nothing obstructs your view. And then you actually have to take a photo of the Messier object through your telescope. And then on that photo, you need to have a date and timestamp and your location to make sure you don't cheat. And the first person that can do it in one observation stretch is the winner. But that also has a lot of timing. So, for example, some Messier objects you can see just before sunset. And for example, if you miss one object, then your timing is out, then you have to restart your observations the following night again. So that means you cannot admire the object. You literally only have to find the object, take a photograph of it, move on to the next object, and take a photograph of it before it sets. And that is the Messier challenge that happens each year. No, I haven't done the Messier challenge. I need a bit more practice for that. Because with that, you need to know the night sky like the palm of your own hand. You need to navigate the night sky. You need to know where these objects are. You need to plan in advance to make sure you can image all of those objects in one go. You will need to hijack a massive telescope. That's true, but you can do it with your own telescope at home as well. I know there's a few people that's actually tried it and a few people that has achieved to do complete the Messier challenge. But at the center of the Orion Nebula, also known as Messier 42, lie four brilliant blue, white O and B stars known as the trapezium, the most luminous in a cluster of a few hundred stars. Surrounding those stars are the glowing filaments of a nebula more than 8 parsecs or 26 light years across. Like a great thundercloud illuminated from within, the churning currents of gas and dust suggest immense power. So what is the most Messier objects found by one person? That is a challenge. So there are few people actually that observed all 110 Messier objects in one night. The significance of the Orion Nebula lies hidden, figuratively and literally beyond the visible nebula. This region is ripe with star formation. So note four important points. The visible nebula is only a small part of a vast dusty molecular cloud. You see the nebula because the larger stars born within it have ionized the gas and driven it outward, breaking out of the molecular cloud. Visual and infrared observations reveal small dusty clouds of gas called Bok globules that may be in the process of forming stars. And secondly, a single very hot and short-lived O star, one of the stars in the trapezium cluster, is almost entirely responsible for producing the ultraviolet photons that ionize the gas and make the nebula glow. The star is so massive that it has already become a main sequence star, while its smaller siblings are still protostars. Then thirdly, infrared observations reveal clear evidence of active star formation deep in the molecular cloud behind the visible nebula. Then lastly, many of the young stars in the Orion Nebula are surrounded by disks of gas and dust. So now we're going to look at contagious star formation. So not only can astronomers locate evidence of star formation, but I also have found evidence that star formation can stimulate more star formation. If a gas cloud produces massive stars, those massive stars ionize the gas nearby and drive it away. Where the intense radiation of gas pushes into surrounding gas, it can compress the gas and trigger more star formation, like a brush fire moving through the interstellar medium. Star formation can spread itself, especially by the actions of massive stars, and astronomers have located signs of such episodes. So here we can see in image A, star forming region N11b. So the blast of light and ultraviolet radiation from the formation of an earlier generation of stars, compressed neighboring gas clouds and triggered the formation of stars at the left side of the frame. Those stars are now triggering the birth of a third generation of stars at the right. So note the Bok globule at the upper right. So here we can see so massive stars in this region were triggered into formation by compression from the formation of earlier stars out in the image to the left. So yeah, these stars are being formed to other stars. And then over here we can see new stars are forming in these dense clouds because of compression from the stars to the left. So these compression are actually forming stars over here. And here we can see the Bok globule. Then in image B, compression can trigger the formation of very massive star clusters. Superstar cluster Westerlund 1 contains approximately 500,000 stars, some extremely massive. It must have formed no more than 5 million years ago. The history of star formation in the constellation of Orion is written in its stars. Judging from the luminosities and estimated masses of the most prominent examples, the stars at Orion's west shoulder are less than 12 million years old, while the stars of Orion's belt are at most 8 million years old. The stars of the trapezium at the center of the Great Nebula are no older than 2 million years. Star formation has swept across Orion from northwest to southeast apparently, beginning near Orion's west shoulder. The massive stars that formed there probably triggered the formation of the stars in Orion's belt. That star formation episode may then have caused the formation of new stars you see today in the Great Nebula. So here we can see the hot trapezium stars, and Earth is this way. This is expanding ionized glass. So here are more protostars that is being formed. So when most of the material in a protostar cocoon has fallen inward or been driven away, the protostar will no longer be quite so hidden. The locations in the HR diagram of protostars that have become detectable at visible wavelengths because their cocoons has disappeared is called the birth line. Once a star crosses the birth line and becomes visible, it continues to contract and move towards the main sequence at a pace that depends on its mass. Stars in this late star stage of formation are sometimes called young stellar objects, or pre-main sequence stars, to distinguish them from earlier protostellar stages. The more massive a star, the stronger its gravity, and therefore the more rapid will be its contraction. Astronomers calculated the Sun took about 30 million years from when its cloud began contracting until it became a main sequence star. But a 30 solar mass star would take only 30,000 years, and a 0.2 solar mass star needs as much as 1 billion years to finish forming and reach the main sequence. So as a contracting molecular cloud core becomes a protostar, the cloud rotates faster and faster. The rapidly spinning core of the cloud must flatten into a spinning disk like a blob of pizza dough spun into the air. So gas from the envelope that has lost some of its orbital velocity through collisions can sink directly to the center of the cloud, where the protostar grows more massive, surrounded by the disk. Other infalling material can add to the disk and then move within the disk plane towards the star. So in this image, we can see the more massive a protostar is, the faster it contracts. A 1 solar mass requires about 30 million years to reach the main sequence. The dashed line is the birth line, where contracting protostars first become visible as they dissipate their surrounding clouds of gas and dust. So compare figure 9.8, which shows the evolution of protostar from about a 1 solar mass as dashed line up to the birth line, and as a solid line from the birth line to the main sequence. So here we can see the birth line of stars. So a 15 solar mass star will take about 0.16 million years, still it starts contracting, becoming a protostar, and actually ending up on the main sequence. And so you can see the bigger a star is, the faster this process. The smaller the star is, the longer this process. So this is now the formation of a protostellar disk. So a slowly rotating cloud of gas begins to contract. Conservation of angular momentum spins the cloud faster and it flattens. Then it forms a growing protostar at the center of a rotating disk of gas and dust. So observations of young stellar objects and protostellar disks introduces three new terms. Star formation regions contain types of stars so young they must have formed recently. T Tauri stars, for example, are understood to relatively low mass protostars ranging from up to 0.5 to 2 solar masses, still in a slowly contracting pre-main sequence phase. Infrared observations reveal the complicated shapes of star-forming clouds that are strongly affected by radiation and winds from nearby massive luminous stars. The formation of massive stars may both foster and disturb the formation of their lower mass siblings. Then number three, in the HR diagram, newborn stars lay between the birth line and the main sequence, with just the properties you would expect of stars that have recently lost their dust cocoons. Young stars tend to have very active hot coronae and chromospheres, making them prominent X-ray sources. Fourthly, observations provide clues about the effects of disks of gas and dust around protostars. These disks evidently cause bipolar flows that push into the surrounding ISM, so interstellar medium, and produce glowing nebula called Herbig-Haro objects. Astronomers also have abundant evidence that these disks are the sites of planet formation. In some cases, dark disks of gas and dust are clearly visible around newborn stars. So in this image, we can see this newly formed star lies at the center of a dense disk of dust and gas that is narrow near the star and thicker further away. Although the star is hidden by the edge on dusty dusk, the star illuminates the inner surface of the disk. Interactions between infalling material and the disk and magnetic fields around the spinning star are hypothesized to eject bipolar jets of gas along the axis of rotation. So these images are cropped to emphasize the upper jet. So arrows indicate knots in the material that have moved noticeably in 2 years. So the artist's impression on the right is to help interpret what can be seen in the Hubble Space Telescope image at the left and center. So do you guys want to take a quick 5-minute break? Okay, so let's take a quick break and we will restart the class at 20 to 7, so 6:40. Yes, that can happen. So later on in this module, we will learn that stars can gain mass, especially in a binary star system where the one star steals basically mass from the other star. Pleasure, but that will be basically an entire section on its own that we will discuss. Okay, let's continue on with this lecture. The detection of these jets was one of the first pieces of evidence that substantial disks often surround protostars. Some evidence of stellar youth is more subtle. An association is a widely distributed star cluster that is not held together by its own gravity. Its stars wander away as the association ages. The constellation Orion, a known region of star formation, is filled with T Tauri stars in a T association. T Tauri stars are approximately low-mass pre-main sequence objects, so OB associations. Fairly obviously are extended groups of more massive O and B stars. The association of stars that are journeying away from each other as we watch are clear evidence of recent star formation. How would you go about making a star? It's simple, really. All you need is something to gather together a star's massive interstellar medium, maybe a light year sized broom, and gravity will do the rest. Contracting the cloud first into a protostar and then into a stable star. The structure of a star is surprisingly simple. So, what keeps a star stable? If there is a single idea in stellar astronomy that can be called crucial, it is the concept of balance. Stars are held together by their own gravity, balanced by the support of their internal heat and pressure. Consider the structure of a star. Using the basic concept of balance, what is meant here by structure is the variation in properties such as temperature, density, pressure, and composition. Between the surface of the star and its center, you can think more easily about stellar structure if you imagine that a star is divided into many concentric shells like those in an onion. You can then focus on the temperature, pressure, and density in each shell. These helpful shells exist only in the imagination. Stars do not actually have such separable layers. So the weight of each layer in a star must be supported by the layers below, so closer to the center. So picture a pyramid of people in a circus stunt. The people in the top row do not have to hold up anybody else. The people in the next row down are holding up the people in the top row, and so on. In a star that is stable, the deeper layers must support the weight of all the layers above. The inside of a star is made up of gas, so the weight pressing down on a layer must be balanced by gas pressure in that layer. If the pressure is too low, the weight from the above will compress and push down the layer. And if the pressure is too high, the layer will expand and lift the layers above. So this stable balance between weight and pressure is called the principle of hydrostatic equilibrium. So here we can see the pressure of the one layer pushing up and the weight of the layer above pushing down. We go to this layer, the pressure pushing up and the weight pushing down. So the star must balance out this process. Is everyone still following? Okay. So the next thing we're going to talk about is energy transport. So how do the different layers transport energy? So the surface of a star radiates light and heat into space and would quickly cool if that energy were not replaced. Because the inside of the star is hotter than the surface, energy must flow outward to the surface where it radiates away. This flow of energy through each shell determines its temperature, which, as you saw earlier, determines how much weight that shell can balance. The movement of energy from the inside to the surface of a star, this plays a crucial role in determining the star's structure. The law of energy transport says that energy must flow from hot regions to cooler regions, either by conduction, convection, or radiation. Conduction is the most familiar form of heat flow. If you hold a bowl of a spoon in a candle flame, The handle of the spoon grows warmer as heat in a form of motion amongst the atoms of the spoon is conducted from atom to atom up the handle. So here we can see the three examples. So conduction, we can see if you heat a part of the spoon, the rest will also get warm. Radiation, it radiates heat away from it. Then we have convection, so warm air will rise, cool air will go down again. Warm air will rise, cool air will go down again. So the three modes by which energy may be transported from the flame of a candle, as shown here, are the three modes of energy transport within a star. Radiation and convection are much more important than conduction in interiors of main sequence stars. So the transport of energy by radiation is another familiar experience. Put your hand in your candle flame and you can feel the heat. What you actually feel are infrared photons, so packets of energy radiated by the flame and absorbed by your hand. So radiation is the principal means of energy transport in interiors of most stars. Photons are absorbed and re-emitted in random directions repeatedly as energy works its way from dark interior toward a cooler surface. The flow of energy by radiation is controlled by the opacity of the gas, so that means its resistance to movement. Opacity, in turn, depends strongly on temperature. A hot gas is more transparent, less opaque than a cool gas. If the opacity is high, radiation cannot flow through the gas easily, and it backs up like water behind a dam. When enough heat's built up, the gas begins to churn as hot gas rises upward and cool gas sinks downward. This heat-driven circulation of a fluid is called convection. The third way energy can move inside a star. You are familiar with convection. The rising wisps of smoke above a candle flame is carried by convection. So now we start to touch on nuclear fusion. So there's a common misconception that the sun's core is hot because nuclear reactions occur there. That statement reverses cause and effect. Rather, it is correct to say the sun and other stars have nuclear reactions in their cores because the temperature is hot enough there. You observe the sun to be stable, therefore it must have a certain temperature, pressure, and density in its core. If somehow you could magically turn off the nuclear reactions in its core, then without a source of energy to replace the luminosity pouring out into space, the sun will gradually lose its internal energy and start slowly contracting again, as was true during the protostellar phase before the nuclear reactions started. So the CNO cycle of a star. So you might expect other stars to fuse hydrogen the same way the sun does, and you would be right for most stars. Some stars, however, fuse hydrogen by another process, and that makes a big difference in their structures. So look carefully at figure 9.15 and study the steps in a CNO cycle. During the process, four protons combine to make a helium nucleus. In other words, the CNO cycle is really hydrogen fusion and has the same outcome as the proton-proton chain, but it is different in important ways. Notice that carbon-12 begins the cycle and ends the cycle. So the carbon-12 nucleus is recycled over and over. Notice also that a CNO cycle includes steps in which protons, so hydrogen nuclei, combine with carbon and nitrogen nuclei. So here we can see the CNO cycle uses carbon-12 as catalyst to combine four hydrogen nuclei to make one helium nucleus plus energy. So the carbon nucleus reappears at the end of the process, ready to start the cycle over again. And now this is probably one of the most important topics of how a star remains stable, and that is the pressure temperature thermostat. So newborn stars contract and heat up until nuclear fusion begins. The energy flowing outward from the core heats the layers of gas, raises the pressure, and stops the contraction. This leads to an interesting question. How does the star manage to make just enough energy to stop contracting, but not to start expanding? The key is the relationship between pressure and temperature. It acts like a thermostat to keep the star burning steadily. Consider what would happen if the reactions begin to produce too much energy. Normally, the nuclear reactions generate just enough energy to balance the inward pull of gravity. If the star makes slightly too much energy, the extra energy flowing out of the star would force its layers to expand slightly, lowering the central temperature and density, and slowing the nuclear reactions until the star regains stability. Thus, a star has a built-in regulator, the pressure-temperature thermostat, that keeps its nuclear reactions from occurring too rapidly. Newborn stars contract and heat up until nuclear fusion begins. The energy flowing outward from the core heats the layers of gas, raises the pressure, and stops the contraction. This leads to an interesting question. How does the star, is this a copy of the previous slides? Yes, this is a copy. So now we're going to look at stellar models. So the laws of stellar structure described in general terms in the previous sections can be written as mathematical equations. By solving those equations, astronomers can build a mathematical model of the inside of a star. If you wanted to build a high-quality model of a star, you would have to divide a star into about 100 concentric shells, and then write down the 4 equations of stellar structure for each shell. You would then have 400 equations that would have 400 unknowns, namely the temperature, density, mass, and energy flow in each shell. Solving 400 equations simultaneously is not easy, and the first such solutions, done by hand before the invention of the electronic computer, took months of work. Now, a properly programmed computer can solve the equations in a few seconds and print a table of numbers that represent the conditions in each shell of the star. Such a table is a stellar model, a mathematical description of the inside of a star. So here we can see our 4 equations. So yes, that is a big matrix that they used, but you don't need to know this equation. These equations, this is just something interesting. So here we can see the center of a star. We have our 100 concentric circles. We have our convective zone and radiation zone. So a stellar model is a table of numbers that represent conditions inside a star. Such tables can be computed using 4 laws of stellar structure. So shown here in equation form, including the principle of hydrostatic equilibrium and the law of energy transport. So the table in this figure describes the present day sun. So this is also an interesting part of computational physics and computational astronomy, where we try to develop better models to model the sun, model different stars. So when a contracting protostar begins to fuse hydrogen, it stops contracting and becomes a stable main sequence star. The most massive stars are so hot that they light up the remaining nearby gas in a beautiful nebula, as if announcing their birth. And after the gas of the nebula disperses, the star begins its long, mostly uneventful life as a main sequence star. In a careful consensus of all stars, including white dwarfs, about 80% are main sequence stars. So what is the relationship between stellar mass, luminosity, and lifetime? Observations of the temperature and luminosities of stars show that main sequence stars obey a simple rule. The more massive a star is, the more luminous it is. That rule, the mass-luminosity relation, is the consequence of the mechanisms causing the stability of main sequence stars. In fact, the mass-luminosity relation is predicted by theories of stellar structure, giving astronomers direct observational confirmation of those theories. So understand the mass-luminosity relation. Recall firstly the principle of hydrostatic equilibrium, which says that pressure balances weight. And secondly, the pressure-temperature thermostat, which regulates energy production. The star that is more massive than the Sun has more weight pressing down on its interior, so the interior must have a higher pressure to balance that weight. That means the massive star's automatic pressure temperature thermostat must keep the gas in its interior hot and the pressure high. The star less massive than the Sun has less weight on its interior and thus needs less internal pressure. Therefore, its pressure temperature thermostat is set to lower. To sum up, massive stars are more luminous because they must make more energy to support more weight. The mass-luminosity relation tells you that a main sequence must have a lower end. Low-mass objects have lower pressures and temperatures in their cores, and those with less than about 0.08 solar mass are too cool to allow hydrogen fusion, called brown dwarfs. Such objects have diameters only about the size of Jupiter, so 10 times the size of Earth. And although they are still warm from contraction, they do not generate energy. So here we can see, when we put this together, we have a small star. So, and here we have a brown dwarf, and here gas giants such as Jupiter. Brown dwarfs fall in the gap between low-mass M stars and massive planets like Jupiter. In the form of new stellar spectral types cooler than M, the warmer brown dwarf falls in spectral class L and the cooler in spectral class T. Brown dwarfs would look dull reddish orange to your eyes, hence the term brown, but they emit most of their energy in the infrared. Brown dwarfs are so cool that liquid and solid particles of silicates, metal, and other minerals can condense to form cloud layers in the atmospheres. Evidently, brown dwarfs have rocks for weather. So to put this into a better perspective, let me show you what is meant with these video of what is meant with these brown dwarfs. So let me quickly just find the video.
The sky, we now know, is full of stars and planets. Stars are massive enough to fuse hydrogen into helium in their cores, generating energy. The heat created by that process tries to expand them, but their gravity balances that outward force, creating an equilibrium. Planets, even gas giants like Jupiter, are far too small to generate fusion. The stuff inside them resists being squeezed, so their gravity is balanced by simple gas pressure. Jupiter is only about 1% the mass needed to have fusion going on in its core. That's a pretty big gap between a big planet and a small star. It's natural to ask, what would happen if we dumped more mass onto Jupiter? Eventually, it would become a star. The pressure in its core would get high enough to initiate hydrogen fusion. But what if we stopped just short of that? What if we have an object far more massive than a planet, but not quite massive enough to become a true star? What sort of thing would we have then? What indeed? By the late 1950s, astronomers were starting to get a pretty good handle on how stars worked. The mathematical equations that govern the physical processes of fusing hydrogen into helium were being worked out and applied to what we knew from observing the stars themselves. In the 1960s, the idea that you could have a star with a minimum mass was becoming clear. If it had less than about 0.075 times the sun's mass, roughly 75 times the mass of Jupiter, it simply lacked the oomph needed to squeeze hydrogen together hard enough to generate fusion. What would such an object look like? Well, it might form like a star, collapsing from a gas cloud just like the sun did 4.6 billion years ago. But instead of turning on and becoming a star, it would simply sit there, cooling. It might start off pretty hot due to the physical forces that made it, but it couldn't sustain that heat. Like a charcoal ember, it would radiate its heat away. After a few billion years, it would be cold, black, and for all intents and purposes, dead. As people started working out what such an object would be like, they tried to come up with a name for them. These things were black and small, but the name black dwarf was already being used for another type of object. Some people called them substellar objects, but that wasn't terribly catchy. Really low mass stars are red, and these new objects would be so cool that they'd emit light in the infrared and almost nothing at all in the visible. So they're somewhere between red and black. Jill Tarter, then a young astronomer working in the field, but who later made a name for herself looking for aliens, and oh boy, we'll get to that later, dubbed them brown dwarfs. She didn't mean it literally, stars can't be brown, but the name stuck. Work proceeded in figuring out what brown dwarfs were like, and a lot of progress was made despite there not being any actual examples of them found. But the hunt was on. Now, as I talked about in episode 26, astronomers classify stars by their temperature. The hottest are O stars, then B stars, which are slightly cooler, down through A, F, G, K, and with the coolest stars being M. But then in 1988, astronomers found a star that was so cool it was distinct from even the M-class stars. It was the first of a new cooler class of stars, so it was given the letter L. Why L? Because there wasn't any other astronomical object that used that letter, so why not? Many more such L stars were found, but still, these weren't true brown dwarfs. These stars were massive enough to initiate fusion in their cores. Worse yet, when brown dwarfs are first born, they're very hot. They can mimic higher mass L stars for a while, looking just like them, making it hard to distinguish between the two. But then a way out was found. A low-mass brown dwarf, it was determined, would have lithium in it, whereas normal stars wouldn't. Lithium is an element, the next one in the periodic table after hydrogen and helium. It can be fused much like hydrogen can, and regular stars would quickly use up their supply of lithium when they were still young. Brown dwarfs, lighter than about 65 times the mass of Jupiter, wouldn't fuse lithium at all. Very careful observations of an object would be able to detect lithium if it were there. That would provide a test to distinguish brown dwarfs from regular stars. The lithium test isn't perfect, but it does work under a lot of circumstances. Astronomers began using it to look for actual, real brown dwarfs. And so they found one. In 1995, a group of astronomers was observing the Pleiades, a nearby cluster of stars that's visible to the naked eye. They were trying to find the faintest stars they could in the cluster to get a complete sample of its membership. The advantage of this is that the distance to the cluster was pretty well known, so a faint star in it must be very low mass. They found an oddball object, which they named Theta 1. It was very red and cool, and best of all, lithium was found in its spectrum. The best models of stellar mass showed that it had about 50 times the mass of Jupiter, or 0.05 times the mass of the Sun. It was clearly substellar. Huzzah! The very first true brown dwarf had been found. At just about the same time, astronomers found that another nearby star, called Gliese 229, had an extremely faint companion. Spectra showed that it was even weirder than Theta 1. It also had lithium and so was clearly a brown dwarf, but its spectrum showed it had methane in its atmosphere. Methane is a delicate molecule and would break down even in the mild heat of Theta 1's atmosphere. This new object, called Gliese 229b, was even cooler than Theta 1. It was looking like we needed yet another letter to classify stars, and so T-dwarfs became a thing. On a personal note, when I worked on Hubble Space Telescope, Gliese 229b was one of our camera's first targets after it was installed on Hubble in 1997. I was lucky enough to work on the spectrum we took of it, and it was freaky. It emitted almost no light in the visible part of the spectrum and rocketed up in the infrared. I'd seen a lot of stellar spectra before, but nothing like this. Remember, Gliese 229b had only been discovered 2 years before. I became so intrigued by it, I wound up studying low-mass stars and brown dwarfs for several years after. Well, it didn't take long before more brown dwarfs were found. In 2009, NASA launched the Wide Field Infrared Survey Explorer, or WISE, an orbiting observatory designed to scan the entire sky looking at infrared light. It found hundreds of brown dwarfs, and now at least 2,000 are known, with more found all the time. Some are so cool that they form yet another classification, Y dwarfs. So now we have O, B, A, F, G, K, M, L, T, and Y. You're on your own for an acronym here. So if brown dwarfs aren't brown, what color are they? Some are so cool they don't emit visible light at all, so they'd be black. You could be right over one and you wouldn't see it. But some are still warm and so give off some visible light, feeble as it might be. What color would they look? Funny thing, they might be magenta. You'd think they'd be really red because of their temperature, but it's a bit more complicated than that. Remember, they have molecules in their atmospheres that absorb specific colors of light. In some brown dwarfs, there are molecules like methane and even water well, steam at those temperatures, that are pretty picky about what colors they absorb. Some of these molecules block more red light than blue, so that messes with their colors, making them look magenta. WISE takes pictures in the infrared, which our eyes can't see. To make pictures, astronomers map each infrared color to one our eyes can see. So an image using the shortest wavelength infrared detector is displayed as blue, the medium wavelength one green, and the longest one red. Brown dwarfs put out a lot of light in the intermediate wavelength WISE sees, so weirdly, they appear green in WISE pictures. That does make them easy to spot in those images, even when thousands of other stars are visible too. The physical nature of brown dwarfs is just as weird as you'd expect. For one thing, they have a very unusual characteristic. As they get more massive, they don't get any bigger. Usually, if you dump mass onto an object, it gets bigger. Take two lumps of clay and smush them together, and you get one more massive, slightly larger lump. Same with planets and stars. But brown dwarfs are different. At their cores, the density is very high, and the physics is a bit different than what you'd expect. The details are complex, but the end result is that when you add more mass to them, they actually get denser, not bigger. This effect becomes important right around the mass of Jupiter, which means that a brown dwarf twice as massive as our biggest planet won't actually be a whole lot bigger. So what's the difference between a small brown dwarf and a really big planet? Well, not much. Nature isn't as picky as we are about having narrowly defined borders between classes of objects. Some people say a planet forms from a disk of material around a star, growing larger as it accretes stuff, while a brown dwarf collapses directly from a cloud of gas and dust. But then you could have two objects the same mass and which look exactly the same, yet one would be a planet and one a brown dwarf, depending on how they formed. That strikes me as inconvenient. Astronomers are still debating this, and it gets worse. For example, as I said before, brown dwarfs over 65 times Jupiter's mass fuse lithium. It turns out that ones more massive than about 13 times Jupiter can also fuse deuterium, an atom that's very similar to hydrogen, except it has a proton and a neutron in its nucleus. But neither of these fuses actual hydrogen, so they're not considered true stars. That's still a little arbitrary, so again, I don't make too much of a fuss about it. I think it's best not to think of them as planets or stars, but something with characteristics of both. For example, the way their atmospheres behave depends a lot on how hot they are. In some, iron is vaporized, a gas. In others, they're just cool enough that iron condenses out of the atmosphere, which means it literally rains molten iron. One more thing. The nearest star to the sun is a red dwarf called Proxima Centauri, which orbits the binary star Alpha Centauri. It's about 4.2 light years away. In 2013, astronomers announced the discovery of a binary pair of brown dwarfs called Luhmann 16. They're only 6.5 light years away and became the third closest known star system to Earth. You gotta wonder, could there be an even fainter, cooler brown dwarf closer to us? We know there's none in our solar system, even out in the Oort cloud. It would have been seen by now by one of several different sky surveys. But a light year or two out? Maybe. Is Proxima Centauri really the closest star, or will we find one even closer? It seems unlikely, but no more unlikely than the existence of brown dwarfs themselves. Maybe sometime soon we'll have to rewrite astronomy textbooks again. Today you learned that brown dwarfs
So that is just an overview of dwarf stars. So let me get back to the lecture slides. So that is where we left off with the slide. So we have a small star, brown dwarfs, and our large planets, our gas giants. So brown dwarfs fall in a gap between low mass M stars and massive planets like Jupiter. In the form of a new spectral type cooler than M, the warmer brown dwarfs form spectral class L and a cooler spectral class T. Brown dwarfs would look like dull reddish orange to your eyes, hence the term brown, but emit most of the energy in the infrared. Brown dwarfs are so cool that liquid and solid particles of silicates, metals, and other minerals can condense to form cloud layers in the atmosphere. Evidently, brown dwarfs has rocks for weather, so as I said, it rains literally molten iron. A star in a main sequence is stable, with its gravity balanced by outflowing energy from fusion hydrogen. The balance must shift as the star consumes its fuel, so that even apparently stable main sequence stars have interiors that are slowly changing. As a main sequence star fuses its hydrogen, 4 hydrogen nuclei are converted into a single helium nuclei, and the total number of particles in its interior decreases. Each newly made helium nucleus exerts the same pressure as one hydrogen nucleus, but because the gas has fewer nuclei, its total pressure is less. This unbalances the gravity pressure stability, and gravity squeezes the core of the star more tightly. As the core slowly contracts, its temperature increases and the nuclear reactions run faster, releasing more energy. This additional energy flowing outward forces the outer layers to expand. As the star becomes gradually larger, it becomes more luminous, and eventually the expansion begins to cool the surface. As a result of these gradual changes in the main sequence stars, the main sequence is not a sharp line across the HR diagram, but rather a band. Stars begin their stable lives fusing hydrogen on the lower edge of this band, which is known as the zero-age main sequence. But gradual changes in luminosity and surface temperature move the stars upward and slightly to the right. By the time they reach the upper edge of the main sequence, they have exhausted nearly all the hydrogen in their centers. Thus, you find main sequence stars positioned throughout the band at various stages of the main sequence lives. So here we can see stars exhausted the last of the hydrogen cores as they have left the main sequence, and here we can see newly formed stars begin life at the lower edge of the main sequence. The Sun is a typical main sequence star. As it undergoes these gradual changes, Earth will suffer. When the Sun began its main sequence life, almost 5 billion years ago, it was only about 70% as luminous as it is now. And by the time it leaves the main sequence in another 6 billion years, the Sun will have twice its present luminosity. Long before that, the rising luminosity of the Sun will drastically modify Earth's climate and ultimately boil our oceans away. Life on Earth will probably not survive these changes in the Sun, but we have a billion years or more to prepare. So here in this diagram, we can see the spectral types, so OBA, the mass, the luminosity, and years on the main sequence. So here we have a reasoning of numbers and another example. So the life expectancies of stars. So you can estimate the amount of time a star spends on the main sequence, so its life expectancy, tau, by estimating the amount of fuel it has and dividing by the rate at which it consumes fuel. So tau equals fuel supply divided by rate of consumption. So the amount of fuel a star has is proportional to its mass m, and the rate at which it uses up its fuel is proportional to its luminosity L. Thus, its life expectancy must be proportional to mass divided by its luminosity. So you can simplify this equation further because, as you saw in reasoning with numbers 8.5, the luminosity of a star depends on its mass raised to the power of 3.5. So now we can substitute it into equation, and here we have the equation of tau equals m over m to the power 3.5, which can simplify it as tau equals 1 divided m to the power 2.5. So if you express the mass in solar masses, the lifetime will be in solar lifetimes. So how long can a 4 solar mass star live? So we have tau equals 1 divided by 4 to the power 2.5, and that equals 1 over 32 solar lifetimes. So solar models showed that a sun, presently 5 billion years old, will last about another 6 billion years. This solar lifetime is approximately 11 billion years, and a 4 solar mass star lasts for about 340 million years. So is everybody happy with this explanation? So this tau is just the symbol we use for this formula. So, ladies and gentlemen, this is the end of tonight's lecture. I hope that you enjoyed the lecture. If you have questions, I will remain active for another minute or two. Otherwise, you're more than welcome to log off. Good luck with the rest of the week, and I will see you all next week in class. And remember, I will be on campus this Thursday for consultation. The semester test will be online. So why do black holes only form at the end of certain stars' lifetimes, but not at the beginning? So that will be discussing that in upcoming chapters. But basically, what happens, depending on the mass of the star, a few things could happen when it's the end of its life cycle. So even it either will become a neutron star, and with neutron star, it has a few different classifications, such as a white dwarf or a pulsar. But if it is above a certain mass, the star at the end of its life cycle will literally fall in on itself and collapse, squeezing it. And that squeezing will cause a singularity, or otherwise known as a black hole. But we will discuss that in great detail later on in this module. It is a pleasure. So, if there's no further questions, I will also log off. Have a great evening, everyone. Have a great week, and I will see you all in next week's class.